Thanks for the introduction, Henry, and hello, everyone. So before diving into the actual topic of this seminar day, I would like to introduce myself and the people that I've been working with. So I am Mohamed, and I'm a second-year PhD student in the computing group. And these are my supervisors. On the ILL side, it's Stefan Holst, and on the side of the University of Southampton, it's Malcolm Levitt and Richard Whitby, and it's a project with quite a lot of people involved, and we've been working on systems that are known as endofullerenes, and we try to do inelastic neutron scattering to determine the potential energy and not. So moving on to the actual topic of the day, I'm going to start by boring everyone by mentioning what a neutron is, again, for the nth time, and then say why they are important in case you were not convinced. And then I'm going to give an image of ultra-cold neutrons and how and where they place themselves on the energy spectrum, and give some examples just to put it into context. And then I will move on to the interaction with matter. Basically, I'm going to talk about the four fundamental forces and how the neutron interacts with it. And I'll talk also about the UCN's most famous property, which is their reflection. And I will wrap up by mentioning some of the ways that you can produce these ultra-cold neutrons. So, well, let's get this one out of the way. Basically, a neutron is a subatomic particle that has no electric charge, but it has a spin of 1/2. And so, and also once they are free neutrons, they can decay due to the weak nuclear force. And a reason why they are important is that since the free neutrons were one of the earliest things that were present in the universe, the rate of decay is the reason why we have some of the various lighter elements in the periodic table nowadays through what's known as Big Bang nucleosynthesis. But for most of us here at the ILL, we just use them as a probe when studying the structure and the properties of different materials, rather than have an interest in the neutron itself. And so for most of us, we are familiar with these quantities, the cold neutrons, the thermal ones, and the hot ones, depending on what kind of experiments you're running at the ILL. But turns out that there is another type of neutrons, which are called ultra-cold neutrons. And first question that would pop into my head was, how cold is ultra-cold, basically? And so turns out it's pretty cold. Basically, their temperature is around 2 millikelvin, meaning that their energy is somewhere in the nano-electron volt region, and they have speeds that you might be able to overtake yourself if you run fast enough, or if you get on your bike, basically. And just to give an image, if your name is Usain Bolt, you can, on your own, run faster than ultra-cold neutrons. Otherwise, just get on your Metro Velo bike and cycle a little bit harder than usual, and you might be able to overtake them, since their speed is 5 to 8 meters per second. And if we look at the gravity interaction, some of them can jump around 2 to 2.5 meters. And in terms of wavelength, it is quite comparable to the size of some viruses that we know. So this was just to give a general image about these ultra-cold neutrons. But the important thing is, since they are so slow and their energy is so low, basically whenever they're going to hit the surface of a material, they are going to reflect reflect instead of penetrate, like the usual neutrons that we use for our experiments. And basically, you can trap them in literal bottles. You know, the bottle is not some sort of abstract physical idea like Schrodinger's cat. It's an actual material bottle where you can just keep them reflecting inside the said bottle. And so now I'm going to move on to their interaction with matter after giving this broad image. Just as a reminder again, their temperature is around 2 millikelvin, and their speed is 5 to 8 meters per second, and their energy is in the order of nano-electron volts. And since we have four fundamental forces, which are the gravity, the weak interaction, the magnetic one, and the strong one, for the first three, I will mention them just in passing, and I will spend more time talking about the strong interaction. Okay, so first step is the gravity one. Basically, you just look up this this formula, and you find out that you get something of the order of 10 to the minus 9 electron volt per meters. Which, if you do a quick calculation, you'll find out that a UCN with an energy inferior or equal to 200 nano electron volts will rise at most 2 meters in Earth's gravitational field. And the way you can exploit this gravity interaction is if you have a falling ultra-cold neutron, you can gain energy, which would help you get those neutrons through detector windows. Second force that I'll be mentioning is the weak interaction. Basically, since a free neutron on its own is not stable, it will decay in around 15 minutes or so. And you might ask then how are neutrons still around in the universe, and I'll get to that in a second. But since they have this decay time of 15 minutes, you could basically, an idea of an experiment, just keep them trapped inside of a bottle for 15 minutes and then reopen this bottle and see if you can get any information about the lifetime of these neutrons. Okay, the third force that I mentioned briefly is the magnetic interaction. Since the neutron has a magnetic moment and it has a spin, you can use magnetic fields to polarize these neutrons. And if you want to achieve 100% polarization, you put them through a 7 Tesla magnetic field. And instead of trapping them in a material bottle, you end up trapping them in what's known as a magnetic bottle. And so the last force that I want to talk about is the strong force. Basically, since they move absurdly slow, they will get reflected off most surfaces. And I've mentioned like 2 slides earlier that these neutrons will decay when outside, when on their own in about 15 minutes. And basically the reason why we still have neutrons is that they are strongly linked to protons inside, to protons. And basically now I'm just going to explain how this, explain is a big word, but still I'll try to explain how the strong interaction works in this case. So since the neutrons and protons are tightly bound inside the nuclei through this strong force, you can basically represent it by a spherical wave potential with a depth of around 40 mega electron volts, which would explain why we still have neutrons since they are tightly bound. And one of the reminders that one of the first things mentioned through this series of seminars is that a neutron which is incident on a solid or on a liquid will see a forest of Dirac function potentials, where A is the bound coherent scattering length of the nucleus at position I. So it's to sum up these couple of slides, and I think I should have just started with this one and moved on to other stuff. Is basically we have 4 fundamental forces, and you have the gravity one, which is easy enough to explain. Then we moved on to the magnetic one. We did not have any electric. We didn't have any electric part in the previous slides. And then the strong nuclear force, what I just said, well, it's strong because it keeps everything bound together. And the weak force is the one that causes the decay, which explains why we have lighter elements in our universe through the decay of these neutrons. So yeah, these were the 4 fundamental forces. But now, if we move on to the reflection of these ultra-cold neutrons, we're going to start off by the potential, which is given by this. And if we solve it, we're going to get a wave function that has 2 parts. The first part is the plane wave of the incident neutron, and the second part is the spherical scattered neutron wave function, which is not exactly true because you are assuming that the incident wave function is the same for every is the same when it comes to the one incident on the whole sample, and when you zoom in on a single nucleus, you are making the assumption that it's the same wave function. But then if you can correct it very quickly, you get something that looks like this, where now there is a new term that appears, which is this n, and it is the the density number of the material that you are using as And if you take this one and apply a couple of mathematical operators, you either rebuild the Schrodinger equation and you get the potential that looks like this now, and it is now a function of this n of r, which is the number density, which depends on the nucleus which is present at position r. Or you build up the wave equation and you extract the refraction index, which is also dependent on this density number. And now this implies that we are in a perfect scenario where there will be no loss, and so we just keep reflecting these ultra-cold neutrons infinitely. But we can make a first assumption, which is assuming that the material is perfectly homogeneous all throughout, and so this density number loses its dependence on the position. So it's just basically just a constant. And on the left-hand side of this table, there's a list of some of the materials that have been used to study these ultra-cold neutrons, and one of the best is nickel 58, which has a potential step of 335 nanoelectron volt and a loss factor that will come back to in a few slides of 8.6 × 5. And so basically now what we have is a potential step where neutrons that will have an energy inferior to the potential at any sort of incidence angle will be always reflected, but always is in quotes because there is a non-zero probability that once these neutrons hit the surface, in this case of E inferior to the potential step, there is a non-zero probability that something goes through. And in the case of E superior to V, there is a non-zero probability that something would still reflect off the potential step. That's why we always in quotes. Okay, so but unfortunately, as I said, we're not in a perfect setting. We're gonna have scenarios where we have a loss of our ultra-cold neutrons while they are bouncing around. The first one is that despite temperature being around 2 millikelvin, the atoms in your material are still going to be vibrating around their equilibrium position. So there is always a possibility that your sample will give a part of its energy to the incident neutron once it makes a transition to another energy state, and then it releases it, and the incident cold neutron will just absorb that, in which case it won't reflect, and it will just go through the material. So that's one way of losing it. And there is there is what's known as a loss probability for each bounce, which is given by this formula. So basically it depends on the loss factor that you can take into account by introducing an imaginary term to your potential and solving the time-dependent Schrodinger equation. And it also depends on your potential step and on the energy of your neutron. And so basically, as you keep bouncing, as time goes on, you'll have more and more probability of losing some of these ultra-cold neutrons. That's the first scenario of where you can lose some of your ultra-cold neutrons. The second one is when you have a reflection, is it a specular one or is it a diffuse one? And there are two ways of looking at it. If you are looking at the neutron guides type of approach, you would like to have the most smooth, the smoothest of surfaces, so you can have specular reflection as much as you can, so you can get through the guide as much as to get through the guide. But if you have a rough surface for your neutron guide, you might have a neutron that will, instead of reflecting the correct way, it will reflect the opposite way and go back, which is not something you would like to have for your which is not something you would like to have for your guides. Whereas if you have a bottle, you having a rough surface, I think will not cause much of a problem for an ultra cold neutron bottle. And so they just keep reflecting inside of the bottle, so it doesn't really cause much trouble if it's a rough surface or not. And the third one, the third scenario of loss is one that I think has been mentioned way too many times during these seminars, so I'm not even going to put a figure for it, which is the inelastic scattering of neutrons. And so your sample gives the energy and you have no more reflection because your cold just goes straight through your material, basically. Okay, so that was for the that was just an overview of the reflection of ultra-cold neutrons. But now, if we go to the production side of things, again, I'll go back a little bit and go to the usual things that most of us know, which is you create the neutrons at the ILL, you free them from the uranium, and you keep a sustainable chain reaction, and then depending on which moderator you have, you're going to have different types of neutrons, either the hot, the thermal, or the cold ones, and they have different energies. And at thermal equilibrium, you have this Maxwell-like distribution. And when you look at it, if you want to know what's the density of neutrons that have a speed in between V and V plus dV, it's something that depends on this parameter alpha, which depends itself on the neutron temperature, and it's mostly dependent on the flux. But that's for the cold, thermal, and hot neutrons. But if you take this expression and move on to the ultra cold neutrons, and you integrate it from a starting energy up to an energy of E equals V, that means that you are looking for the density of neutrons that can be trapped inside of a potential that has the walls as high as this V value. And you have this expression at the end. So it depends on your thermal flux. So basically it depends on how much neutrons you have at a temperature, a certain temperature when it is at equilibrium. And so again, this still does not talk about how you manage to create these ultra-cold neutrons, but one way you could do it is you create your free neutrons, then moderate it until they're in the cold region, and then you make them downscatter in a medium that does not absorb them. One such medium is superfluid helium, where you just let it scatter in here, and you're going to be creating acoustic vibrations like phonons and sound waves, and it's just going to keep scattering in here until it becomes an ultra-cold neutron. That's one way of doing it. Another way of doing it here at the ILL is by using a vertical extraction with a guide that starts off straight and then it's a bit bent, where basically you have a straight guide that goes into the cold source. So you have incident neutrons that have a speed of 50 meters per second and a thermal flux of 1014 neutron centimeters squared per second. So basically you're vertically enhancing them through the straight, vertically extracting them through this straight guide, which is 5 meters long and made of nickel. And so as they keep rising, they're going to keep losing their energy as they go up. And then they're going to reach the bench part, which is even longer, and it's 30 meters long. And its job is basically take out the fastened neutrons and the gamma rays out of your beam. And then after that, we go from the 50 meters per second down to a speed of 4 to 15 meters per second. But you're not done yet. You go in through a turbine that has 250 turns per minute, and through these collisions with the turbine, they're going to keep losing. Going to keep losing energy, and at the end of the day, you'll end up with a neutron that's with a speed that's 5 meters per second, and then you can use them for your different experiments. So now that you've produced your ultra-cold neutrons, I would like to wrap up with a list of a couple of experiments that can be done and that will be talked about in the next presentations. Mostly you can do some neutron lifetime measurements when you have a material bottle that traps the UCN, or the magnetic bottle that has them trapped inside of it. You can also do experiments that are looking for the dipole moments of the neutron, or you can go more exotic and go to gravitational levels and search for dark energy. And I believe that that's about it. And I would like to thank Tobias and Oliver for giving us a reference that was quite complete about ultra-cold neutrons. And I would like to thank you again for tuning in, despite the weather,